that promotes this so-called Godonov numerical flux that is guaranteed to give me a physical solution to the problem. It is still a first order scheme. It is still a first order scheme, but it is the good first order scheme. Alright. So what is a Godonov flux scheme? A Godonov flux scheme is the numerical flux that gives you the physical solution. And how does it work? It works by analytically solving the so-called Riemann's problem. So I'm going to the Riemann's problem is a problem that starts with a u left and u right and the discontinuity in the middle. And the Riemann's problem can be solved analytically. Okay? And particularly, we only need to solve the Riemann's problem for infinitesimal time. And then, so this is u at t. And the Godonov flux is looking for the interface flux at the same point after an infinitesimal time. So let's draw u of t plus epsilon. What the solution is going to be like. So let's say this is at exactly x plus half. And there are several cases. Let's concentrate on the Burger's equation for several cases. Okay, case 1. Case 1, u left greater than 0 and u right greater than 0. What is going to happen after infinitesimal time? Which direction is the solution moving towards? Towards the right, right? I don't care if this guy stays as a discontinuity or becomes an expansion. Anyway, it is going towards the right. So after infinitesimal time, I get something like that. This can be a discontinuity, can be an expansion. But the solution at the interface after infinitesimal time is what? Wait, what is the solution at xi plus half after infinitesimal time? UL, right. And that is the value of the Godonov numerical flux. That is f of UL. So f of I plus 1 half is equal to f of UL. The Godonov flux basically takes the correct flux, takes the flux of the analytical solution after infinitesimal time. Okay, so this is only one of the cases. Case 2 is when the whole solution moves towards the right, towards the left. And in that case, what should be the Godonov flux? UR, f of UR, because the whole solution is moving towards the left. Okay, and here I'm going to actually take a slight. Okay. So let's stick to the Burger's equation and generalize later on. So this is the case where I'm having something like this after infinitesimal time. So the solution here, after a while, is going to be UR, and I should be looking at f of UR. So what are the other cases? Let's do green. Case 3 is UL is less than 0, less than UR. So now UL and UR are different signs. In that case, what happens? What happens after infinitesimal time? What is the physical solution?
It spreads.
It spreads. right? It spreads. So the solution would become like that after a little bit. Now here's the most critical question in Godonov flux. What is the value of the solution at the interface after infinitesimal time? I would have you look at the physical solution again. If this is the discontinuity, what is the value of the solution at this line after infinitesimal time? Average of the two? So if UL is equal to minus 0.001 and UR is equal to 10,000, is the solution here going to be the average of these two? What is special about the solution here? Remember, the characteristics are straight lines, right? If the solution here is a certain value, the characteristic here should be going towards one direction or the other. What is the value of this straight line over here? Huh? df du, right? And for Burger's equation, df du equal to u, right? So the slope is df du. And what's special about the slope here if I draw a vertical line? Infinite? Yeah, which corresponds to df du equal to 0. Information stays. Yeah, this is correspond to the value of the solution where the characteristic stays straight. df du equal to 0, or u is equal to 0 for Burger's equation. Okay. So in case 3, after infinitesimal time, the solution here, this is actually 0. The expansion fan expands around the 0 solution. If the right is higher than the left, then the right is going to expand further away. The center of the expansion is always going to be 0. And f of u in that case, f of the Godonov flux, should be what? Should be what? 0, yes. It's f of 0 is 0. Okay. Any questions on this case? We get to one last case. Any question on this case? This is actually the most tricky case to figure out in Godonov's scheme, actually in the Riemann solver, in the Riemann problem.
Just for the Burger's equation.
Just for the Burger's equation. Let's generalize in the next lecture. Yeah. Any other questions? Okay. Case 4 is UL greater than 0 greater than UR. I said case 3 is the most tricky case. Case 4 is the second most tricky case. Okay. In this case, do we have an expansion or a shock? A shock. Which direction is the shock moving?
Delta F over
delta F over delta U, right. So f of I plus half should be either UL or UR depending on which direction the shock is moving. Okay, it depends on the half of UL and UR, which is the speed of the shock, greater or less than 1 in this case. 0. Greater or less than 0. Greater than 0, the thing is moving towards the right, then I should take UL, right? So this is the This is the case. The shock is, we have a shock and shock is moving towards the right. And we should be taking UR. Well, f of UL, f of UR. If UL plus UR over 2 is less than 0. Okay. That's it. That's all the 4 cases in Godonov scheme. And if we stick to that, we get a fancier version of the upwinding scheme, right? I mean, case 1 and case 2 are basically upwinding, but case 3 and case 4, I mean, case 4 is also a fancy version of upwinding, except for case 3, where it is not. And when you stick to Godonov scheme, we get the physical solution all the time. Okay, so let's start from the next lecture, generalizing this to more general conservation laws, and then go to second order. You have a question?
Yeah. Is the physical solution unique?
Is the?
For the Berger equation?
Yes.
Are there only 2 solutions, or there are infinite number of solutions?
Oh, there are infinite.
Is it possible that we can have like 3 physical solutions?
The physical solution is unique. The non-physical solutions can have many different things. You can also have things like half expansion, but at some point it starts to stop the expansion like this, right? So there are infinitely many non-physical solutions, but there is only one physical solution.
And so the physical solution is always regular, smooth at t0 plus dt.
The physical solution is, it's not always smooth, but like because if you switch the 1 and -1 to the other way, you stay as a shock wave. Yeah. But the physical solution has no characteristic emanating from any discontinuity. That's the criteria. All right. Okay, so I'm having office hour right now. I'm going to my office, 37447. All right. Oh, thank you for the keyboard.
Yeah, no worries. Isn't some book that talks about how you can look at the discrete operator and that's doing the entropy or anything something like this? The first question I asked, like you said, basically the scheme has to kind of mimic what the actual physics are doing.
Yes.
It's like I've not thought of it in that way, and I'm like, I feel like it would help. Like maybe people are like, all right, the scheme needs to conserve energy or destroy energy, or conserve energy, destroy energy.
Right. I've never read a book that discusses about that. There is a word that is used to describe like numerical mimicking the behavior of a physical solution. It's called a mimetic. Like if you have a scheme that mimics the behavior of the physical solution, it's called a mimetic scheme.
So a mimetic scheme, M-I-M-A-T-S.
Yes, yes.
And if I look that up, I would see a discussion about that.
Yeah, there are different aspects. Like for example, conservation of entropy is one aspect. There are also, like in fluid dynamics, there are also schemes that conserve vorticity, for example. Vorticity is it's not. I mean, if you just look at the governing equation, you can't immediately. It is not obvious the solution is going to conserve vorticity, but through some analysis, if you manipulate the differential equation in particular ways, you're going to see, oh, it conserves vorticity. Now, like entropy is similar. Like if you know the solution is continuous, smooth, you're going to see the solution conserves entropy. Only when you have a shock wave, you know, like entropy is no longer conserved. So these are properties of the analytical differential equation that like it's not obvious from the definition, but you can derive these properties. And mimetic schemes tries to discretize the governing equation in such a way that it still have these properties.
But it has to be in a discrete sense, right? Like when it acts on
In
a
a discrete
vector,
sense, yes.
it will conserve that
Exactly,
property.
exactly.
Okay.
So that's exactly in the discrete sense.
Yeah,
Yeah.
I'm actually trying to make